Hello. Today I'm going to talk about how to secure the compilation process. A brief introduction about myself. I'm Alice, and I'm a second-year PhD student working at the Secure Systems Lab, New York University, and I'm advised by Professor Justin Couples. I'm also a maintainer of the Lean project, which focuses on the system virtualization. Today, I'm going to first talk about the current problems of compilation security, then introduce our framework that can mitigate this problem, and finally, we will show one prototype based on this. The software supply chain has multiple stages. It starts from retrieving and reviewing the source code, then goes through the compilation, packaging, and the final distribution. Lots of efforts have been made to ensure the security of each individual steps and the end-to-end supply chain security. For instance, tools like Git and GitHub help ensure the security of the source code and review process. TUF and Upton ensure secure software delivery, and frameworks like Salsa and in-toto provide end-to-end supply chain guarantees. But the compilation stage is still relatively underprotected. Nowadays, more and more attacks are targeting on the compilation pipeline. One of the most noticeable attacks is the SolarWinds attack in 2020. Attackers planted a tiny helper on the build server. It just sat there watching for the build to start. After compilation starts, it quietly swapped a legit source file with malicious one, and then swiped the real file back. Reviewers looking at the repo but saw nothing unusual. The change only existed during the compilation. Another example is 3CX attack. Attackers first compromised an employee's machine through a poignant third-party application, then moved laterally into the company's network and onto the build machine and signing host. From there, this slipped malicious libraries into the build process. So the installer shipped with malicious components, but still signed with legit certificate. So defenses have to sell the build environment itself and produce evidence of exactly what is executed during the compilation, not just check the source and sign at the end. Currently, we have several solutions for the secure compilation. The first one is in-toto, which provides signed and verifiable attestation report. Another one is the sales build track, which defines the assurance level for build pipeline. Those techniques ensures the source code or build script and the compilers are trustworthy, but they can't address issues related to the build environment itself. So why is still hard to make the compilation environment safe? The first reason is that it's hard to create secure build time environment. If we want to compile 5 lines Hello World program, we choose a compiler toolchain and get our final binary. It may seem that we only need to trust the compiler toolchain we choose, but in reality, every operation during the compilation depends on the underlying operating system. And the operating system itself interacts with the hardware. And the hardware also has lots of components. So in the end, we are really trusting the entire software stack. And even in the Ubuntu minimal, there are over 400 packages installed in that. Then even if we are only compile 5-line program, the trusted computing base is super large. We need to trust the compiler toolchain, the operating system kernel and services, and also the hardware or the firmwares. And each layer of the software stack is based on its own trust assumptions. So if we want to defend the attacks during the compilation, we need to consider not only the attacks related to the compiler toolchain, but also we need to consider the hardware attacks and the attacks based targeting on the operating system. The second reason is that it's hard to maintain trust in large-scale, complex compiler toolchains. Like I mentioned before, an operating system usually has hundreds of packages, and during the compilation, each package relies on the same complex software stack, and that makes it really hard to trace where the root of trust actually starts, and even harder to ensure that trust is securely carried through the entire chain. One current solution to mitigate this problem is a reproducible build. Reproducible build is to run the same build pipeline multiple times, and then compare the final binary. If the final binary are identical, then we believe the build pipeline and the final binary are trustworthy. But the reproducible build also faces several limitations or the issues. The first one is that the reproducible build needs to ensure at least one builder is trustworthy. Second, more than one party need to have access to the source code. And also the benign environmental differences will cause the final binary different, and that will increase the overhead for audit. And the most important issue of a reproducible build is that it still relies on same complex build environment. So it doesn't actually solve the issues related to the build environment. Another solution is the hermetic build, which runs in isolated sandboxed container or virtual machines and can produce deterministic results. Builds depends on known version of build tools, such as compilers, dependencies, and libraries. But the limitation of the hermetic build is that we can't audit compilation behaviors or the build environment. We still need to run multiple times to verify the outputs. So currently, we are still lacking an auditable and practical solution. We propose the secure and auditable framework to mitigate the previous problem called Trisale. Trisale is consisted by 3 auditable components. Here's an overview of the Trisale. We put a minimal runtime into the hardware protected execution environment. And in the runtime, we've implemented a syscall. It will have a syscall mediation layer that can redirect all the syscalls during the compilation process to the in-memory file system to achieve so that it doesn't have any interactions to the outside world. And from high level, it will only have two types of calls, one for input and setups, and another one is output. All the communication are happened through the controlled channel. Here is the system's perspective. The tri-cell is located at the hardware level, and since tri-cell can log all the operations, make all the operations happen just inside our environment. So it won't interact with the host operating system, which also means any malicious behaviors or unintended behaviors in the REST OS won't influence the compilation process. And we've also implemented a prototype for the tri-cell. The trusted computing base is significantly smaller than the regular software stack, and our environment can also and tri-cell can also generate the attestation report to make the process and the environment auditable. So next, I will talk about our prototypes. The prototype is based on several current techniques. The first one is the Intel SGX enclave, which provides a hardware protected execution environment. And the second one is the SGX remote attestation, which let a verifier can confirm the code is executing inside a valid enclave with guarantees. And the third one is the in-toto attestation, a framework that can generate the attestation report, which can record the what's actually happened between different steps during the compilation. And the fourth technique is a WebAssembly, which is a portable, safe, near-native execution of untrusted code across platform in a sandbox. So our prototype is used previous techniques to create an isolated and auditable environment, which provides a practical solution for secure compilation. So in our prototype, we use the customized Watson time as our minimal runtime, and the Intel SGX as our execution environment. And we've implemented the POSIX feature to make it compatible with the legacy Linux applications, and also a system call mediation layer that can redirect syscalls or blocking calls to achieve non-interactive build environment. Here's the execution flow of the tri-cell. There are three phases for the build with tri-cell. First, in the first stage, when the user will first create an SGX enclave through the tri-cell CLI using a configuration file to specify runtime and build parameters, which trigger the enclave initialization. Next, the Wasm runtime is launched inside the enclave. Instantiate the enclave in-memory file system, preloading required compilation files, and the in-toto tools and the compilers into the in-memory file system. After we finish loading everything and set up all those stuff for the tri-cell, the syscall mediation layer will block any calls other than the file system calls. And all the file system calls will be redirected to the in-memory file system in the phase 3. And during the third phase, the in-toto tools will also record all the intermediate and final build artifacts to make sure that all steps are confined to the trusted environment. Currently, our prototype supports a tiny C compiler called TinyCC to run inside the enclave with in-memory file system, and the produced binary can be run on the native Linux. Here from the screenshot, we can see the TOMO file is a configuration file that can specify the parameters and for the build pipelines. Okay, thank you. Do you have questions?
I had a quick question on the hardware layer with this lives. Is there like specific boards you have to support?
Sorry, could you say again?
Sure. Is it just Intel specific for the SGX piece, or can I use like other boards in part of the full stack kind of like board, electrical engineer, firmware team, software team?
Currently, our prototype only supports the SGX.
Okay.
But theoretically, we think it's portable to other hardware execution environment.